Okay, folks, so in the last few videos we've seen both the increasing decreasing test and now the first derivative test. And so putting those two tests together, we can now come up with ways of determining where we have local maximums and minimums on a function. So this kind of completes the question that we started way back in section 4.1, where we said, how do we find the extreme values of a function? And in 4.1 we gave a technique for finding the absolute max and the absolute min of a function. But now we have tools for finding the local max and local min for a function, and that is to use this first derivative test. That'll be one way we can do it. So let's go ahead and get started. The first thing we're going to do is let's get the domain of f. And the domain of f in this case is all real numbers. That's really nice. The second thing we're going to do is we're going to find the critical numbers of f. So let's go ahead and do that. Let's go ahead and find f prime of x. We're finding the first derivative. We get 12x squared plus 6x minus 6. Notice that the derivative is defined everywhere. So we're not going to get any critical numbers from the derivative being undefined. But where might we get critical numbers? Well, we might get critical numbers from the derivative being 0. So let's see where if it's ever 0. And let's see what we end up with. So I can go ahead and factor a 6 out of the polynomial on the left. So we get 6 times 2x squared plus x minus 1. So that leaves us with 2x and x. And I think I want this to be plus 1, and I want this to be minus 1. Let's just double check that. Let's see, that would give us 2x squared, yes, plus 2x minus x, yes, I think we're good. So that means that we have critical numbers at x equals a half and at x equals minus 1. Those are our two critical numbers. So now what do? Well, this part's the same as what I had you do in those earlier steps. We're going to draw ourselves a number line. And on the number line, we're going to put any places where the function was undefined, in addition to any critical numbers of the first derivative. Okay. So any boundary, I should be a little more careful, any boundary points of the domain or any places where we have critical numbers of the first derivative. So in this case, we've got a critical number at -1 and a critical number at a half. And as I've encouraged you to do, let's label these whether they're critical numbers or they're because the function's undefined there or something else. Okay. So now we run through the same procedure as before. Let's go ahead and take test points. So I need something to the left of -1. A good choice for that might be -2. I need something between -1 and 1/2. So I pick 0. And I need something to the right of positive a half. So let's pick 1. So then I'm going to look at f prime of the test point. Okay. As we've seen, I'm not going to actually evaluate -2 in the derivative. I'm just going to say what will be the sign on the derivative if I were to plug in -2. And we see here if I plug -2 into this factor right here, I'd have -2 plus 1, which is a negative number. If I plug -2 into this factor right here, I'd have -4 minus 1. Okay, that's another negative number. And then times this positive factor. So we've got a negative times a negative times a positive. The result of those three products is again a positive, so the function is increasing before we get to -1. If we were to plug in 0, this factor would be positive, this factor would be negative, this factor would be positive. We'd find that we're decreasing on that interval. And if I plug in 1, let's see here, this factor will be positive, this factor, everything will be positive here, and so we end up with this. So in previous questions, we would then say, well, we can now give the intervals for which f is increasing, -infinity to -1, and 1/2 to infinity. We could give the intervals for which f is decreasing. Where is f decreasing? From x equals -1 to x equals 1/2. The new thing in this section now is we can go ahead and state where we have local maximums and local minimums on this function. And it turns out that we've got a local min at x equals 1/2. This was by the first derivative test. How do we see that? Well, what was the function doing before it got to the x value of 1/2? The function was decreasing, then it arrived at the x value of 1/2, and then it left it and it was increasing. And notice that 1/2 is a place where this function was defined. So I know there's not a hole there, I know there's not a vertical asymptote there, and so that means that x equals 1/2 is a local minimum. Likewise, we can see that we have a local max at x equals -1. How come? Because before I got to -1, the function was increasing. After I left -1, the function was decreasing, and the function was defined at -1. Okay. Now, the derivative may not be defined at -1. I could have a cusp at -1, or I could have a corner at -1, but the function's defined there, so I don't have a hole, I don't have a vertical asymptote, so that means that I must have a local maximum at x equals -1. Okay. I think what I'll leave you to do is I'll leave you to try example number 10 on your own. Now I'm asking you to find all extrema on number 10. Okay? So not only are you going to look for local maxes and local mins, you're also going to look for global maxes and global mins, and you've developed tools for doing that. Okay? So to help you out, I've gone ahead and I believe down here at the bottom I gave you a graph, but you should be able to answer the question without the graph. So let me just give you your steps and I'll leave you to finish this out. Step 1, as always, give the domain of f. Step 2, give the critical numbers of f. Step 3, find local maxes and mins. Okay. To do that, see number 9 above. And then step 4 is to do something you've already done a number of times, find the global max and mins. Okay. And that's using the techniques that we did in section 4.1. So I'll leave you to finish out this problem. Give it your best shot. If you don't get it completely, that's okay. We'll try it again in class tomorrow, but I do want to see that you've attempted this. All right, thank you very much, and we'll see you in class.